Yes, ma'am. Ma'am, please start the recording. Yeah, yeah. Now it's
It
started.
started. Okay,
Yes.
so I have with me my co-instructor Karthik. I think he'll be joining in a moment. Okay, no problem. I'll just share my screen and we'll get started. Okay, I'll unmute all of you. So if, in case if you have any doubt, so you can ask. Okay. I hope I'm clear, like I'm audible, and you can share, you can see the screen as well.
Yes, ma'am. It's clear.
All right. So this is lecture 0A. So we'll go through some of the commands in Octave. It is very much similar to MATLAB, but right now our focus is to first understand what is a matrix. Okay, why do we need metrics? Why you are studying math? So I'll just motivate you. So if you have, you are a suppose a student, okay, and we want to just a second. So student, you have to store the marks of a student, marks in one subject, marks in, I'll write here, marks in one subject, marks in the second subject, then marks in the third subject. So this is the vector. So this is suppose student one. Student one marks are like 10. Then you have 20 in second subject. Third subject, it's suppose 40. So this is the marks of first student. Okay, so matrix of the first row. So matrix is the array of numbers. So this is first vector. Okay, first row. First row will store the details of the first student. Second row will store the details of the second student. And third row will store the details of the third student. Okay, and if you want to predict, or you can say, uh, now I'll just tell you how it applies to ML, machine learning. Suppose you want to predict the price of a house. Okay, so first row. So you have house one data. So it will store, price of a house. Okay, sorry, just a second. First, so first row will is a data. It's a feature vector. It's a vector, right? Row vector. You call it a vector. This represents the, say, number of rooms. This represents the area of the house. Now suppose this represents the price of the house. Now based on the number of rooms and the area of the house, you have to predict the price of the house. So I'm just taking one very toy example. Similarly, you have second row. This is the row. Okay, second row represents the second house. Again, this will represent some, number of rooms in the second house. Then the number of, then this is the area of the house and this is the price of the house. Okay. So you have to, in machine learning, what you have to do, you have to find the relationship between the this price, how price is connected with the number of rooms and the area of the house. There could be many, many more values, like this is number of rooms, area of the house, or you can say another feature could be the proximity to the airport. Okay. So, this matrix will contain the details about, many houses, say 10,000 houses, you have collected the details. Okay, so in machine learning, it's about you have to predict or find the, relationship between the price of the house and the number of rooms, how price is connected with the number of rooms and the area of the house. You can have many, many other examples. Like, for example, you want to predict whether bank, should give a loan to a customer or not. Now, so the last column, this is a column. This is one column. So here, this matrix has 3 columns. Okay. Suppose now you want to predict Now I'm just giving you motivation why you should study maths, how it is related to ML, because this is you are studying MTech AI ML. Okay. Now suppose there is a customer one. Okay. Customer one. Now bank wants to predict whether it should give a loan to the customer or not. Okay. So here this column, it is just 1 or 0. Means 1 means loan should be given, or it could be 0. 0 means loan should not be given. Now what are these? What should be these values? The salary, it could be, salary of a customer, or it could be like degree of a customer. What is the profession? Okay, you can say designation of a person, customer. So now whether the loan should be given or not, it depends on the salary and the designation. Right now I'm taking only two feature, but two values. Okay, but there can be many other factors also that determines whether the customer should be given loan or not. So you have to predict, you have to somehow, find the pattern. Like, okay, so you ultimately your goal is to find what is the pattern of a person who should get a loan. So you should find a pattern. Okay, what should be the salary like? What should be the designation like? Okay. So basically, ultimate goal is like you are representing your data. So this is your first customer. First row means first customer. Second row means second customer. So if you have 10,000 customers, so your matrix will contain 10,000 rows. Okay. Uh, so that's why you are studying matrix, because ultimately every real life problem, it boils down to numerical vector. Okay. A numerical matrix or vector. Okay. So these are the entries. So this is a rectangular array. So the number of rows here in the first matrix is 2, and the number of columns is 1, 2, and 3. Okay, so 3 columns. So this matrix is 2 into 3. You call it as 2 into 3. Okay. Now you have, so this matrix is having 3 rows. 1, 2, 3. So 3 rows and 3 columns. If matrix has m rows and n columns, so it should be written as m cross n matrix. Okay, this represents the rows. This represents the columns. Okay. Now this is a matrix having just one row. So you call it as a row vector. So this is one row. So 1 into 3. So this is a special type of a matrix. So it is called a row vector because there is just one row. Okay. And so this is represented as one row into like 3 columns. Now come to this. Now here you have 3 rows and 1 column. So it should dimension should be 3 into 1. Okay. So this I've already told you, like this is A matrix A. So A11, this is the row number. The first index means the row number. This is the column number. So this entry means A11 means it's the element of a matrix present in first row and first column. Similarly, consider A12. A12 first index means it's the row. 2 means it's the column. Okay. Similarly, A1n. 1 means the row and n means the column. So this A1n is the entry in the first row and nth column. Similarly, if you have this M1, so this is the mth row and the first column. Okay, this AM2 is the entry of mth row and the second column. So you can have, okay, so this matrix contains the details about the M customers. Okay, so first row represents the first customer, second row represents the second customer, and the mth row will represent the mth customer. Now in Octave, how will you represent it? I'll just come to it in the end. I hope you can see. Slides are visible, right? Why it is called a vector, not a scalar? I think I've enabled your mics. You can speak if you want.
So vector has both magnitude and direction.
Yeah,
Scalar
why
is a
not? Why?
single value.
Yeah. So you are asking why it is called a vector, not a scalar. Scalar is just one value. For example, you can say for this is, you are asking here why this is called a vector, because it is not a scalar. See, scalar is just one value, whether it is 4, this is a scalar. This is just one value, 5, some real number value. Okay. So this is a vector because it is either a row or a column. Okay, now consider this. So vector is a matrix with only one row or one column. So for example, this is a row vector because it is only containing one row. Okay, one row and n column. So 1 into n. Okay, so suppose this. Now consider this. This is a column vector because it is just having one column. There are m entries. So this is m into 1. Okay, so this is having suppose 3 values here. B is having 3 values. So this is the column vector because it is represented as a column. It is having 3 rows and 1 column, 3 into 1. Okay. So this is
Ma'am, can I
a,
ask? Actually, I asked this question. This is Abhishek. So you are mentioning since it has multiple values in the row, so that's why it's a vector. But we know
yeah.
like vector has a like value and as well as direction. So where this direction coming from means uh, why it is vector means why I'm not actually understanding means where is the direction mentioned over here?
So direction is like direction you cannot see. Don't okay. You are just comparing with I, J, third 3 dimension that you have studied, I, J, K, right?
Yeah,
Correct.
physics.
Physics. So this is extended. See, it's IJK. So it was 3 dimensional. You saw, when you studied in 11th or 12th vectors. But now 3 dimensional can is extended to, see here it is 5. So this is that like we are here. We don't talk about the directions. Okay. So here we just talk about, okay, suppose this is the, you can say, okay, for example, here 412. Suppose this is the column vector. It represents, suppose, the person salary in lakhs. This represents, so here we are not talking about the directions. We are just talking about the values in every dimension. In every dimension. Suppose this is 4 is a person's salary in lakhs. First, first value. Okay, this is the value indicating, okay, uh, whether the person has got his own house or not. To represent something else. Okay. So here we don't talk about the directions. Okay. Now, when do you say the two matrices are equal? When, see, if you have two matrices A and B, when they are said to be equal? When both have the same entries. So, for example, if A is, I'll go to Octave also and explain. Yeah, you are right, Athitan. I'll just go to Octave also. Octave online. You can also say on open it online. Suppose I write A. You can open it online also. A is suppose. How do you represent matrix? 1, 2, 3, semicolon. Semicolon is a way to go to another row. 4, 5, 6. So this is your matrix A. See, this is your matrix A. Okay. I've just opened Octave online. Okay. I want to show you the equality of the matrix. Actually, my tab is not working. So I have to explain. I'll explain here. B is also the same matrix. 1, 2, 3, semicolon, 4, 5, 6. Okay, B. See, A is also this matrix. It is having 2 rows. There are 2 rows in A and 3 columns in A. B is also having two rows and 3 columns. So both are having the same number of rows, same number of columns, and all the entries are identical. See, 1, 2, 3, 4, 5, 6. B entry is also the same. So you say both the matrices, they are equal. Okay. So when do you say two matrices are equal? When both the matrices, they have same number of rows and same number of columns. Also, every entry is the same. Every entry means A11 is same as B11, A12 is same as B12, and so on. Hello? Yeah, please mute. Okay, now we have to do addition of matrix. Now, why, like, when do you say two matrices can be added? So you can add two matrices if both are of the same size. That means both should contain the same number of columns and same number of rows. For example, if A contains 3 rows and 4 columns, 3 into 4, then B also should contain 3 rows and 4 columns. Okay, then only you can add. So for example, if I have an octave, see, I don't know why this is opening. Okay, let's say, okay, B is this. Suppose C is, I have another matrix C. C is suppose a 9, 7, 2, semicolon, then 1, 5, 6. Okay, so C is this. See, B is this, C is this. Now, both B and C, they have same number of rows, which is 2. C is also having 2 number of rows, and B is having 3 columns. C is also having 3 columns. So B and C should like they have the same size. Now, if I want to add, I can just do B plus C. See, B plus C. So what is this? 1 plus 9 is 10. 2 plus 7 is 9. Okay. 3 plus 2 is 5. Okay. Then you have 4 plus 1 is 5. B plus C. 5 plus 5 is 10. Then you have 6 plus 6 is 12. Okay. Is it okay? I've added B plus C. B is this. C is this. Okay, now. Okay, fine. Now let's see some of the properties. A plus B is same as B plus A. That means if I plug in A first and then B, the result is same as if I put B first and then A. Because so it is called commutative. So you can see B plus C is same as C plus B. I'll just show. So this is B plus C. I'll show you C plus B also. I should add something. इससे कर, let's do. This is simpler, I guess. Oh God, these ads are hell. Okay, we'll focus here. 1, 2, 3, semicolon, 5, 4, 5, 7. A is this. B is. So I have to execute this. So A is this. Okay. Now let's type what is B. B is 4, 5, 8, 9, 10, 11, something. So both. Now if I execute this, so the A is this, B is this. Now I have to separate two rows by semicolon. Now if I just type A plus B and B plus A, so both will give me the same result. Execute. See, see, this is your A plus B and B plus A. So this addition operation is commutative. It is commutative because both will give the same result. This is A plus B. You're adding each entry. Entry by entry, you are doing addition. 1 plus 4 is 5. 2 plus 5 is 7. 3 plus 8 is 11. So this is done entry wise. Okay. Now comes this. Now you are doing the scalar multiplication. That means you are multiplying by a number, the sum of matrices. So see this. Should I show you or you will explore? Come on, tell me. Where is this? When will you plot row in M? Okay. I'll do. Don't worry. What is this scalar multiplication? That means I have to tell you what is this. See, C is the scalar. Okay, C is some value, some real number. Okay. So that's why it's called scalar multiplication. You are multiplying the sum of two matrices. Okay, and you are saying that this, when you do the sum and then multiply with the scalar, the result is same as the multiplication of first matrix by a scalar and adding it to the CB. That means you are multiplying second matrix also with a scalar and then you are adding. So the result of LHS is same as result of RHS. Okay, I'll show you. Don't worry. See, maths is not difficult, so don't get scared. Okay, where is okay? So let's do that. Okay. Now I'll say C. C is some scalar. I say C is say 2. C is a scalar. It is just a real number, some real number. Okay. Now if I say C A plus B, C of A plus B, what is the value? See, let's calculate. C of A plus B. First we'll say, okay, A plus B. Let's
Okay.
execute.
So the C will be multiplied with all the entries out of A plus B, the output from A plus B.
Yeah.
Okay, this is your A, this is your B. Okay, and then first you add A plus B. So A plus B is this. You are adding entry wise 4 plus 1, 5, 2 plus 5, 7. That I already told you. Now you have to multiply with C. Now scalar multiplication means you have to multiply every entry of A plus B. This is A plus B. Every entry of A plus B with this scalar C. C is 2. So 2 into 5 is 10. Okay. 2 into 7 is 14. Okay. 2 into 11 is 22. Okay. Then 2 into 9 is 18. Oh, sorry. 2 into 13 is this is A plus B. So you have got, okay, C into A plus B is this. So 2 into 15 is 30. 2 into 18 is 36. All right. Now if I say C into A, what do you think it will give? C into 8. Can you tell me? What will happen to C into A? You are multiplying scalar C with the whole matrix A. Can you tell me what will happen?
1, 4,
The
6,
element will be
8,
multiplied by
10,
two.
Yeah,
14.
yeah, everything will be multiplied by 3.
Each
4,
element
6,
will be multiplied by
8, 10, and 14.
Each element will be
So
multiplied with
let's
C.
see. Let's see. I should print also now. Print or disk. What is it? Let me just try.
2, 4, 6. 8,
So
10.
that you know the result now. I hope it's fine.
That's correct.
Let's see it works or not. हाँ, अच्छा ठीक है. Okay, I'll do one thing. Now I have to do this of then I'll have C star A plus C star B. Yeah. So now what we have done is first we have multiplied scalar with the addition of two matrices. Okay, let's see. I hope it gives all the results within one screen. Acha, theek hai, let's maximize it. This is your A. This is your B. A plus B is this. Actually, it is not showing the result in whole screen. Acha, theek hai, I'll just display this and this. Then you will visualize. है ना semicolon लिख देती हूँ. Okay, this needs to be semicolon. Semicolon if you put, then it will not be displayed. A plus B let's display. हाँ ये भी display कर देते हैं. Okay.
ठीक है भाई.
ये लिख देते हैं ऊपर. ठीक है. Now let's see. See A plus B is this. Okay. Then you multiply each entry with C. So you got this. Okay. And then now this entries is equal to C into A plus C into B. C into A you compute That means you multiply every entry of A with C and then you add it to C into B. That means you multiply every entry of B with C and then add with this C into A. So see, the result is going to be the same. Is it okay? Any doubt? Acha, you people are already doing. That's good. Yeah, vector is a matrix with either one row or just one column. That's correct. And scalar is a matrix. Scalar is, don't call it a matrix. It's just a real number, okay? Or you can say, yeah, it's a special matrix with one row and one column. That's it, with one value. Okay.
Okay. Got it.
I hope my co-instructor is also there who will just see the chats. Karthik, are you okay? Thank you, Karthik. Okay. Now the thing is, A plus, when you add three matrices. So first you have to add two matrices, then add its result here. For example, here, see, add the result of this two matrices addition, two matrix addition with the third matrix. So the result is going to be the same as when you add the second and third matrix and then you add it to the result you will get added to the first matrix. Okay, so this is called associativity. I'll just show. Okay. So I'll just clear it. Okay, A is this, B is this. Now I'll have some matrix C. C. Let's see what is. You give me the values. Okay. Now we have to see whether it is associative or not. So let's add first two matrices. A plus B plus C.
It will be.
I hope you know how what is the addition now. Addition of two matrices. Okay. Now okay, now let me just execute it. So see the result, A plus B. So here you are adding two matrices first. So when you add these two matrices, so your A, let me show you what are your A and B. A, B, C. Okay. This is your A, B, and C. See, this is your A, this is your B, this is your C. So when you add first, here it means you add A and B first. So you add the entry wise entry. 1 plus 4 is 5. Okay, 2 plus 5 is 7. 3 plus 8 is, I'll show you. Okay, 3 plus 8 is 11. Then 4 plus 9 is 13. 5 plus 10 is 15. 7 plus 11 is 18. Now you add the result of A plus B with the C. You get this. Here that means you are adding A and B first and then you are adding C. And here it means you are adding B and C first and then you are adding to A. Is it okay? Addition, so this is called associativity. We have done this rule now. We have done this rule. Now let's do this rule. This rule says when you add the two scalars, okay, add the two, C and K are two scalars, you add them and then multiply with the matrix. So the result is going to be the same as you multiply C with A, you multiply first scalar with A, multiply the second scalar by A and then add the results. This I'll show you. Okay. So here, see, suppose A is this, C is say 5, some scalar. K is 2, some scalar. Now you say C plus K, add the two scalars. See, scalar addition is allowed. You know, scalar multiplication is also allowed. Now this is made. So now you are doing, you are adding C plus K. This is 7. And then you are multiplying with A. That means every entry of the matrix A will get multiplied with the 7. So this result, let's see what is the result. See, this is your A. Then you are adding C plus K. You are adding the scalars. 5 plus 2 is 7. And then you are multiplying with every entry of A. So 7 into 1 is 7. 7 into 2 is 14. 7 into 3 is 21. 7 into 4 is 28. Okay, 7 into 5 is 35. 7 into 7 is 49. Okay, so this is, now this result will be the same as C into A plus K into A. That means you multiply C with A first. Then you multiply K with A first. Okay, this is your second step. And now you add the result. Add the result. Let's see. So this is your, okay, it is going down. Let me just do semicolon. Semicolon. Okay, I'll just show you this. So this is C plus K into A. You're adding C plus K, 5 plus 2, 7, and then you're multiplying with every entry of A. So 7 into 1 is 7, 7 into 2 is 14, 7 into 3 is 21. Next, now I'm saying this is same as C into A plus K into A. That means you multiply first scalar with A. Okay. Then you multiply second scalar with A and then you do the addition. So this result will be the same. C into A plus K into A is same as this. Just see. This is your C plus K into A. C is 2, C is 5, K is 2. So 7 into A. So this is this result. Now this is C into A. C is 5. 5 into A will be 5 into 1 is 5. 5 2s are 10. 5 3s are 15. Then 5 4s are 20. 5 5s are 25. You are multiplying every entry of A with the C. C is 5. Okay. Now, second thing is K into A. You multiply every entry of A with the K. K is 2. So 2 into 1 is 2. 2 into 2 is 4. 2 into 3 is 6. 2 into 4 is 8. 2 into 5 is 10. 2 into 7 is 14. So this is C into A. This is K into A. Now you do the addition. So 5 plus 2 is 7. 10 plus 4 is 14. 15 plus 6 is 21 and so on. So this is We have done B rule completely. This we have done. Okay, now A plus 0. See, 0 is not a scalar 0. Please see. You cannot add a scalar with a matrix. That won't be compatible. This is a 0 matrix. Okay. A plus 0 is A. I'll show you. So 0, how do you represent? Suppose B is a matrix of zeros. Zeros. You write it like this. Zeros of how many rows? It should be there. 2 rows and 3 columns. So you say A plus, oh sorry, B is a 0 matrix. B plus A. Let's execute. I don't know why it is. See. So 0 matrix, how will you write like this? Zeros. 2 rows and 3 columns. So this means 2 rows. See, B has 2 rows, 3 columns, all zeros. So if you do addition, you will get the same matrix A. 1 plus 0 is 1, 2 plus 0 is 2, 3 plus 0 is 3, 4 plus 0 is 4, 5 plus 0 is 5, 7 plus 0 is 7. Okay, now let's go ahead. Similarly, you have, now here what you are doing is C into K. See this rule. C into, first you multiply scalar K with A. That means you multiply every entry of A with scalar K and then you multiply with C. The result will be same as this. That means you multiply C and K first and then multiply with A. Okay, so I'll just show you. Suppose C is 2, K is 3. So I'm saying you multiply C and K first. So first on the left hand side we have see, now we have to verify this. This one. First you multiply K with A and then you multiply with C. C. C you multiply with K. K into A is so this is K into A. Okay. Now you multiply with K into A is K is 3. So every entry of A gets multiplied with 3. 3 into 1 is 3. 3 into 2 is 6. 3 into 3 is 9. Then 3 into 4, 12. 3 into 5, 15. 3 into 7 is 21. Okay. Now you multiply with this KA with the C. This matrix, now you have to multiply with the C. See. So this is your KA. KA means K is 3, A is this matrix. You multiply every entry of A with K and then you multiply KA, this matrix with C. So 2 into 3, 6, 2 into 6, 12, 9 into 2, 18, 12 into 2, 24, 15 into 2, 30, 21 into 2, 42. Okay. Now this result is same as this C into K multiplied with matrix A. That means C into K is 6. 6, 6. So you should get 6 into 1. I'll show you. See, both this is what? This is this. C into K is 6. So now you multiply every matrix entry by 6. So 6 into 1 is 6. 6 into 2 is 12. 6 into 3 is 18. 6 into 4 is 24. 6 into 5 is 30. 6 into 7 is 42. So this result is same as C into K into A. So here you're multiplying scalars first, and then you're multiplying that result with A. Every entry of A is getting multiplied with C into K. And here what you are doing is you are multiplying first A, like every entry of A with the K, you get this. Okay, and then you are multiplying it with, you are multiplying the entry of every entry of this matrix with C. So result is going to be the same. See, both the result are same. All right. Next we have A plus minus A is equal to this 0. Don't get confused with the 0. This is not a scalar. This is a vector, or this is going to be the matrix only. So when you add A with the minus A means you multiply every entry of A with the minus 1. So you will get the 0. This is not a 0 scalar. It's a matrix. Okay. So let me show you. Again, it's very easy to verify. So this is going to, if A is this, okay, A plus minus A. So let's see what is the result. It's going to be the 0 matrix of 2 rows and 3 columns. Okay, now you have this 1 into A. This is 1 into A. Now this is 1 is a scalar. That means you multiply every entry of matrix A with 1. So you'll get the same matrix. So this is the we talked about the algebra of matrix. Okay, now comes the important operation, matrix multiplication. Now here first we have to see when is the matrix multiplication compatible. So why do you need to do the matrix multiplication? See, you will do this in the neural networks, deep learning. So there also you have to do matrix multiplication. That's why we are studying it here. Okay, so when do you say two matrices can be multiplied? First, you have to see. Don't get bogged down by these notations. Just don't worry. Ignore. I'll tell you. I'll simplify it. So when do you say two matrices are multiplication compatible? When you have the number of columns in the first matrix, if it is equal to the number of rows of the second matrix, only then the two matrices can be multiplied. So when you multiply two matrices, so you will get the resultant matrices having m rows and p columns. So p is the column of B and m is the number of rows of A. So for example, if you have A matrices 2 cross 4, 2 m is 2, n is 4. So if you want B to be compatible with A, so it should be n should be 4 and P could be anything. P could be say 3. So now the resultant matrix will be M is this, M cross P, 2 cross 3. So this is 2 cross 3. Okay, let's see. Now here what do you do is you are multiplying AB. So A is 3 by 3. B is also 3 by 3. 3 rows, 3 columns. B is also having 3 rows and 3 columns. Now take the first. Now this is the result answer. Now how do you get it? So this is the first 1 entry, 1 entry, right? A1, C11. This is matrix C. So this is C11. C11 means this index means take the first row of A. Okay, multiply it with this first column of B. Okay, so what do you get? So 3 into 2. So 3 into 2 is 6 plus 5 into 5 is 25. 3 into 2 is 6 plus 5 into 5 is 25. And this into this minus 1 into 9. So this is going to be 31 minus 9. It is 22. Okay. Now comes the, see, this is 3 cross 3. A is 3 cross 3. And B is how many rows? 3 cross 4. So the resultant matrix has to be 3 cross 4. Resultant means the answer matrix. So this is your M. M is 3. N is 3. So this is your N. N is 3. So same. The number of columns in A is same as the number of rows in B, which is 3. And P is 4. So here the result will be M cross P. M cross P. 3 rows and 4 columns. Okay. Now I have verified this entry, right? Now let's verify. So that means my resultant matrix C will have 3 rows and 4 columns. Now let me tell you how will you get this entry. This entry is 2 second row and third column. This is second row and third column. So what will you take? You will take the second row of A, because first means you have to take the second row of A. This corresponding to the row of A. Second row of A, take its dot product with the third column of B. Sorry. This is the second. Again, this is second. I'll take some different. Let's take, okay, first I'll do for this. This is second row and the third column. How will you get 14? This is C23 entry. This is 2. This is 3. Second row and third column, right? This is third column, second row. So here you have to take the second row of A, take its dot product with the third column of B. How will you take dot product? So 4 into 3 is 12. 12 plus 0 into 7 is 0. Plus 2 into 1 is 4. 2 into 1 is 2. So it is going to be 12 plus 2. So it's going to be 14. Okay, let me derive this entry. Can you tell me how this is coming? Okay, you tell me now. How will you get this entry? Tell me. Are you people there?
Yeah, third
Third
row of first matrix. Is
अच्छा
the
3 है ना ये simple है. Let me give you some this. Let's see how this ends. So this is third row and which column?
second column.
हाँ ठीक है. Now which row will of A will you take?
-6, -3,
-6
Third row.
into -2
Third row.
Third row of A.
And
plus -3 into 0 plus
And second
-4
column
Second
of
row
into
of B.
second.
Second column of B.
Okay, let's take. What will you take now?
12 minus 8 is 4.
-6 into -2, 12.
Plus
12
-3 into
minus 8.
0
So you
plus 2 into -4.
4. You are getting 4. 12 minus. देखो ना.
Yes.
Let's see. -6 into -2, 12. -3 into 0 is 0. 12 minus 8, 4. So this is correct. Similarly, you can evaluate all the entries. You can check for 26 how you are getting. You want to check or should we go to next?
Ma'am, why is BA not defined?
Very good question. Why B is not defined? See, B is, what is the dimension of B?
3 cross 4.
3 cross 4.
No, to perform matrix multiplication, the inner dimension must match. Otherwise, we cannot do matrix multiplication. Right, so that's the criteria.
Very good. Now see, BA, why it is not defined? Because here the number of columns of B is not the same as number of rows of A. I told you now when matrix multiplication is compatible. When you say why A and B matrix multiplication is compatible, because this is number of columns of A is same as the number of rows of B. Is it okay?
Yes.
That's the reason BA is not defined. All right.
If the sizes of A and B are the same, even then BA is not defined.
What? Sorry,
If the
come
sizes
again.
of A and B if the sizes of A and B are the same, let's say it's 3 by 3 and 3 by 3, even then BA is not defined, right?
No,
No,
then you
then
can
see,
do.
No, then
it is
No,
same
we
now.
can
This is
perform
same as this.
multiplication, but will it be the same number? I mean, sorry, it's not defined, it is defined, but would it be the same matrix in
The,
the
yeah,
results?
the resultant matrix will be the outer dimension, right? Because it is the
3 cross
resultant
3.
matrix. Yeah.
Yeah. This is your M. This is your P. So the resultant matrix will also be M cross P now.
Yes, yes, it's
See.
defined. I agree, it's defined. My question is, will the result be equal matrices for AB and BA?
Equal means suppose 3A is 3 cross 2. Okay, B is also 3 cross 2. Though both are having the same sizes, but they are not compatible as far as multiplication is concerned. Reason, this is the number of columns of A. It is not equal to the number of rows of B. So AB is not defined. Okay.
So if we multiply a row vector with a column vector, we just get a
Ah.
single digit, right?
Yes, yes, yes. Suppose A is, you can say now. Okay, I'm feeling it very difficult to write because I'm handicapped, like feeling handicapped because of the tab is not working. Okay, let's see, let's solve your point. A is a row vector, suppose 1, 2, 3, and B is a column vector. Okay, B is a 4, 5, 6. Okay, let's not A, B is this. A is a row vector, B is a column vector. Now, so A is a special type of matrix because it's a row vector. Okay, so what is the dimension? It is 1 row into 3 columns, 1 into 3. And this is 3 into 1. So the result has to be when you say AB. So result will be just, this is 1 into 3.
1 cross 1.
1, yeah. So 1 into 1 cross 1, 1 into 4 plus 2 into 5 is 1 into 4 is 4, 2 plus 5 is 10, 10 plus 4 is 14, plus 3 into 6 is 18, 14 plus 18 is 32. I hope it's fine.
No, it is fine, but just we were initially talking, right? When it comes to a single digit, it becomes a scalar.
No,
Single
in case
digit.
of matrix multiplication, A dot B is not equal to B dot A, even though their dimensions are same.
Yes. See, it's not every time if A and B they are of same sizes. It's not that A into B will be defined because A is matrix of say 3 cross 2. B is also 3 cross 2. But you cannot multiply them because A is 3 by 2, B is also 3 by 2. So number of columns of A, which is 2, is not matching with the number of rows of A, number of rows of B. Okay, I'll tell you. Yeah, you got it now?
Yeah.
Okay. Acha. Now matrix multiplication is not commutative. That means A into B is not equal to B into A. Let's see. Why? See. This is your A. This is your B. Now first we have to, A and B both are 2 cross 2. So matrix multiplication is compatible. 2 cross 2. Because number of rows of A, which is 2, is same as the number of columns. Oh, sorry. Number of columns of A is same as the number of rows of B. So they are compatible. And the resultant matrix will be 2 cross 2. Why 2 cross 2? Because here, this is coming from the number of rows of A, which is this. And this comes from the number of columns of B. Okay. Now let's do the multiplication. So first, this is 1 comma 1 element. 1 comma 1 element, how will you get? By multiplying first row. This index refers to the first row of A. This index refers to the first column. Multiply. So 1 into minus 1 is minus 1 plus 1 into 1 is 0. Okay, you get 0. Now come here. This entry. This entry is 1 comma 2. First row and the second column. Now this entry is 1 comma 2, right? First row and the second call. This 2 means take the second column. Second. So this is 1 into 1. Okay. Plus 1 into minus 1. So this is 0. Okay. Now come here. 2 in comma 1. 2 means take the second row. Just a second. 2 comma 1. 2 means take the second row of A. Here 1 means take the first column of B. 100 into minus 1 is minus 100 plus 100 into 1 is 100. So minus 100 plus 100 is 0. Now come this. Now this is 2 comma 2. 2 comma 2 means this refers to the row of A. This refers to the column of B. Take the second column of A and take its dot product with the second column of B. So again, you'll get the same result. 100 into 1 plus 100 into minus 1. This is 0. So this is the 0 matrix. So this is your A into B. A into B is a 0 matrix. But when you compute it, B into A. B into A is also compatible multiplication because B is 2 cross 2, A is also 2 cross 2. So when both the matrices, they have the same number of rows, it is 2. They are square matrices having the number of rows is same as number of columns. So when you have such type of matrix, when you're multiplying with such two matrices of that type, then it is compatible. Because here number of rows is 2, number of columns is 2, both are same. And the second matrix also, number of rows is same as number of columns, which is same as the first matrix. Okay, now let's do the multiplication. Okay, this is 1 1 entry. 1 1 entry means, sorry, just a second. 1 comma 1. For take the first row of A. This is take the first column of B. Then do the dot product. Dot product is do the element by element multiplication. And then you add. Minus 1 into 1 is minus 1. Plus 1 into 100 is 100. 100 minus 1 is 99. Now go to the second. This is one first row and the second column. Okay, so here that means this first row means take the first row of A. Now we are looking at this point, this 1 comma 2. Take the first row of A and multiply with the second column of B. So minus 1 into 1 plus 100 into 1. So 99. Okay, now you will tell me how do you get this? What is this element? Don't feel shy. This is
Second row and second row
column.
of first matrix and first column of second matrix.
So what will you get? Tell me what is the value?
One minus 100. That is
Yeah.
99 minus.
Minus 99. Similarly, you can do this. This is what will you take?
The second row of first matrix and second column of second matrix. Two.
Great. So what will you get? 1 into
Minus 99. 1 to 1, 1 minus 100. Minus 99.
Okay. Now, there is one interesting observation. Observation is, see, when you multiply two matrices, if the result is 0, see, AB, when you multiply A with B, the result is you're getting 0 matrix. But it is not implying that either A is 0 or B is 0, right? Neither A is 0 nor B is 0. Agree or not? See,
Yes.
what is the result? This line is saying, even if the product of two matrices is 0, it does not imply that like A is 0 or B is 0. Okay, so this is the, so 2 points here you are two interpretation of this slide is, two interpretations of these slide are, first is matrix multiplication is not commutative. Second observation is if the product of two matrices is 0, it will not imply that A is 0 or B is 0. See, both are non-zero matrices, A and B, but still their product is 0. Okay. Okay, now you take the transposition.
So-
What do you mean by?
So in any case, the product will be not,
Changing row to
commutative.
column. Right?
Column row or column?
Hello?
Yeah, I'm listening. Please tell me.
Yeah, so in any case, we will not get, commutative result for the multiplication, is it? Or for the square matrix, it
No,
is
no,
there.
whether it is
When
square
the
or
matrix is identical, in that case,
Yeah.
you will see the commutative result. Both the matrices are equal.
what?
No, it will be better
Acha,
see.
okay, okay. You are saying if A is this 1, 2, 3, 4, suppose. Like if A you are multiplying with A,
In that case, it would be,
it
that
will be
anyway, it's
same
an,
as both are equal now. Or when you have say A into I is identity matrix.
identity matrix. Yeah, okay. Got it.
Then
Thank
only this is commutative.
Ma'am,
Yeah,
also
yeah.
in the first example, like 1 1 and 100 in that example, if your second matrix remains same, that -1 1 1 -1, if the first matrix, if you make it anything like 2 2 99 99, every time it will be 0.
2,
It
2,
is
99, 90. It is going to be 0. Yeah.
because the second matrix is such that -1, it is such a symmetric matrix. I don't know what to say, that every time when you multiply
Identity
with
matrix.
it will be 0 always.
Yeah. Correct. Provided you have such type of entries, like first row,
Yeah.
all the entries are same. Second row, all the entries are same.
Yeah.
Isn't it? Okay. Good observation. Okay, let's go to the transpose. Transpose converts row vector to column vector and conversely. Now I'll explain in the octave. Let's see. Okay. A is suppose 1, 4, 7, 7, 8, 2. So transposition. So this is a A. Okay, I'll show you A. A is this. Now if you take A transpose. Transpose or transposition, whatever you can say. So here you have to do like this. Notation is this in octave. So here what will happen is, I'll just show you first. So here what happens is, first row will become the first column. So when you take the transpose, so first row will become the first column, 147. Second row will become the second column. Okay. Or you can say like this. The first column of A, which is 17, it will become the first row of A. Second column, which is consisting of 4, 8, it will become the second row of in the transpose. Similarly, the third column, 7, 2, it becomes the third row. So row in original matrix is a column in the transpose. See, this is the first row. It becomes the first column in the transpose. Similarly, if you have 7, 8, 2, this is the second row entry. It will become the second column entry in the transpose. So this is the concept of transpose. Okay. Now let's see some properties. It says that when you take the transpose of A and again you take the transpose, so you will get the original matrix A. For example, here. So this is your A transpose. Now you again take its transpose. Suppose this is your B. Okay. Now you take again the transpose of B. You'll get the same matrix. I'll show you why. So this is your A. You take its transpose, which is this. Now you again take you again take its transpose. So what will happen? The first row of B will become the first column 1 7. Second row of B will become the second column 4 8. Third row of B, it will become the third column. So basically this is B. Okay, and you are taking its transpose. Right? So here what we did was so we have A. Okay, then we compute A transpose. This is same as B. Okay, now you take B transpose. So when you take B transpose again, you will get original matrix. Okay, is it fine?
Yes, ma'am.
Okay. Now you have the third property. Third property is saying when you add the two matrices and then you take the transpose, so the result is going to be the same. Let me use this placer. When you add two matrices, take its transpose, the result is going to be the same as addition of the transpose matrix. Let me tell you how this is coming. Okay, so this is your A. Okay, suppose B is 2 5 6 8 9 1. Okay, then you have A plus B transpose. Then you have A transpose plus B transpose. Now let's see whether these two results are same or not. I don't know why it is colored. So let's check. Okay, this is your A. This is your B. Okay, now you add both. First, let me show you A plus B as well. See, this is A, this is B. You add 1 plus 2 is 3. 4 plus 5 is 9. 7 plus 6 is 13. Okay, 7 plus 8 is 15. 8 plus 9 is 17. 2 plus 1 is 3. Okay, this is your A plus B. Now you take its transpose as we have to do A plus B transpose. This is A plus B, take its transpose. So first row will become the first column. 3 9 13. Second row will become the second column. Okay, now what about this? Now let me just. So this is your A plus B transpose. Result is same as A transpose plus B transpose. You can check. What is A transpose? Okay, you record these values somewhere. Write down in your notebook. This is A plus B transpose. Now we'll do this. A transpose. B transpose. Okay, this is the A transpose, this is the B transpose. How to go down? Acha, हाँ. A, B. This is a A transpose. 1 7. First column will become your, okay, you can say first row will become your first column in transpose. This is your A transpose. Second row of A will become column in the second column in A transpose. Now same with B. First row will become the first row in B becomes the first column in its transpose. Second row of B will become the second column in the transpose. Now this is A transpose, this is B transpose. Now you have to add. So result is 3, 2 plus 1 is 3, 7 plus 8 is 15, 4 plus 5 is 9. 8 plus 9 is 17. 7 plus 6 is 13. Okay, 2 plus 1 is 3. You got it? Is it okay? This is A transpose plus B transpose. A transpose plus B transpose. Now I also showed you this result. Oh, now this result is same as A plus B, then A plus B transpose. Okay. This is your A plus B. This is your A, this is your B. A plus B is 2 plus 1, 3, 4 plus 5, 9. 7 plus 6 is 13. Now you take its transpose, A plus B transpose. What do you get? First row is 3. This A transpose plus B transpose is this. Then you have A plus B. Just a second. Okay. So this is your A plus B. Its transpose is same as, so first row is same as the first column. 3, 9, 13. Second row is same as second column. I am not able to show you because of the space. Take second. Okay, you got the concept? Okay, I'll try it once more.
We got it, I think.
Oh, no, don't say I think.
No. I think I added because of for others.
Acha, acha. Okay. Okay, no problem. No, okay, I'll just see the chat screen. Okay, people are saying yes. I hope you are following the lecture.
Yes, ma'am.
Okay, now comes. Okay, next is C into A. C is some scalar. See, if you take C some value like 4, 5, whatever it is, if you take its transpose, it's going to be the same scalar. Okay, let me try to prove this, like validate. See, I'm not doing the formal proofs. It's not required actually, because you just need to understand the concepts. That's it. Okay, let's see this. C into A, you take the whole transpose. Now we'll do this rule. This C into A, you multiply scalar with matrix, then take its transpose. It's same as take the scalar and multiply with A transpose. Now I'll show you. Okay. Okay, this is your A. C is supposed to. Okay. Now we say C into A, whole transpose. That means you multiply C with A. So it is going to be 2, 8. Okay, first I'll show you what is C into A. Then we have C into A transpose. Oh, sorry. A is this, multiply C with A, you just multiply every entry of A with the scalar C. That is 2. So 2, 8, 14, 14, 16, 4. And then you have to take its transpose as per this. So what do you get? First row will become the first column, 2, 8, 14. Second row will become the second column in the transpose. So this is C into A whole transpose. Now it says that this is same as, that means it says take C out, scalar out, and then you take the transpose, multiply C with the transpose of A. Let's see. So the result is going to be the same. See, you are taking A transpose. So A transpose is going to be like, okay, first I'll show you what is A transpose. A transpose. Okay, then you say C into A transpose. See, this is your A, this is your C, and this is third step is this C into A whole transpose. Okay, this is same as I have to prove this is equal to C into A whole transpose is equal to C into A transpose. That means you take C out, okay, and then take the transpose of A. So then I took the transpose of A and then multiply with the C. So 2 into 1 is 2, 2 into 7 is 14, 2 into 4 is 8, 2 into 8 is 16. So see, this result is C into A transpose. And this is, we have already calculated, this is C into A whole transpose. That means you multiply A with C first. 2 into 1 is 2, 2 into 4 is 8, 2 into 7 is 14, and then you take its transpose. So you'll get this. All right, okay, this is important because this one, like in fact, all these properties are important. Now this is the most important because it will be used in later on in the course. So that is if you take the product of two matrices and then take its transpose. So the result will be same as B transpose into A transpose. That means you reverse the order. So here you are multiplying like A first, then you are doing B, then you multiply and take the transpose. So the result will be same as this B transpose. Here the order is reversed. First you are putting B transpose and then A transpose. So let me just show it to you. Okay, suppose A is this. A is this. Now let's make because we are multiplying. So let's take the compatible. So this is matrix A is this matrix A is 2 cross 3. So let's take B to be some 3 cross 2. 3 rows. 1, 2, and we'll take 2 columns. So let's say what is this A, whether this is compatible. This is 2 rows, 3 columns. 2 into 3. B is 3 into 2. So number of columns in A is same as number of rows in B. So this is compatible. So now let's take the transpose. A into B. Take the transpose. So that means you multiply A into B. You multiply both the matrices and then take the transpose. Why it is typing twice? Something. Okay. And then it is same as B transpose into A transpose. See, this is A into B. You multiply A into B first and then take its transpose. Result is this. It is same as first you take B transpose and then you multiply with A transpose. Okay. I hope you can do the multiplication. Is that fine?
Yes, ma'am.
Yes,
Okay.
yeah, clear.
Okay, now comes the, okay, this is, we have done. Okay, now comes the special type of matrices. Why these are important? Because these are very much helpful in machine learning, symmetric type of matrix. Symmetric means when you take the transpose of this matrix, A transpose, you should get the same matrix A. A transpose is equal to A. Okay, take its transpose. So what will you get? Is this symmetric matrix? No. Why this is not symmetric? Because if you take its transpose, what will you get?
Something different, not the same.
Yeah, you are getting 1, 1, minus 1. 1, 1, minus 1. Because first row will become first column. But the first column of A transpose is not equal to the first column of A. So they are not equal. A transpose is not equal to A. So you'll say that this matrix is not symmetric. I'll give you one example of symmetric matrix. 1, 2. Now if you take its transpose, what will you get? A transpose is same as A. So first row is this 1, 2. So it will become the first column 1, 2. Second row is 2, 3. It becomes the second column 2, 3. So here the A transpose, you can see it's same as A. So that means that it is symmetric. They have special property. You will see when you study, eigenvalues, eigenvector. Okay, now comes the skew symmetric. Skew symmetric means when you take the transpose of A, you will get the negative of A. Okay, when you take the transpose of matrix A, you should get the negative.
Ma'am, I have one doubt.
Yes, yes, please tell me.
In the first one, that -1 AJI equal to AIJ, but that how is that -1?
Actually, this is not symmetric. If you want it to be symmetric, keep it +1. There is a typo here. Okay.
Okay, okay.
So this has to be +1 if you want it to be symmetric. Now you can just take the transpose. This is +1. If you take the transpose, so first row is becoming the, let's take the transpose of this. So first row becomes the first column. Okay. Then second row will become the second column. 1, 2, 0. Okay. Third row becomes the third column. So which is 1, 0, and 5. Okay. So now you see whether these two matrices are equal or not. They're equal. So this is your A transpose. A transpose is same as A. So you call this matrix to be symmetric. All right?
Got it. Got it. Just that -1, I was having that doubt.
No, it was typo.
Okay.
Oh, we will correct it. Okay. Now comes the skew symmetric. Skew symmetric means Aij is equal to minus Aj. It means, so here you are reversing the order. Aij is C. Here, see, Aij is Aj. That means row index is I. It becomes the column. J is the column. Column becomes the row. Okay. Okay. Now comes the skew symmetric. Skew symmetric means A transpose should be equal to minus A. Okay, A transpose should be equal to minus A. Now let me check its transpose. So let's compute the transpose of this. Okay, tell me what is the transpose. So first row will become first. What will be the first column?
0, 1, minus 2.
0, 1, minus 2.
Yes. What is the second column?
-1, 0, 3.
Then what is the third column?
2, minus 3, 0.
Now, can you say that A transpose is minus of A? Minus of A means when you multiply every matrix of every entry of A with -1. So
Yes.
minus A will be what? -0 is same as 0, -1. Then minus or -2 will become 2. So this is okay. Then so minus of -1 is 1. -0 is 0. Then -3 is okay, -3. Then -2. So A transpose is same as minus of A. Then you say it is skew symmetric. Okay, now let me ask you one question. What is the important observation about the skew symmetric matrix? Can you observe something?
Diagonal elements should be 0, I guess.
Very good observation. Diagonal, see, if diagonal element is any, if you find any diagonal element to be non-zero, you can straight away say that it cannot be skew symmetric. Okay. So this is one important observation. I'll tell you how it can be proved also. Now, see, Aij
Ma'am,
is,
if it is not 0, but if it is 1, 1, 1,
you'd say 1. Okay, 1, 1, 1.
ah, yeah,
Then it won't be skew symmetric
Minus
now.
AJ.
The minus will not work.
Because 80, you take the transpose. This property will not be satisfied. You take its transpose. You can check now. So this is 1, 1, 1 minus 2. So here it will become first column 1, 1 minus 2. Then second row is minus
minus
1,
minus 1, 1,
1,
3,
then 2
It will be
2 minus 3, 1,
1. Now
2
you
minus
check.
3, 1.
Now you check. Is this equal to minus A? See, if this is minus A, then
Yes.
here also. So this is not equal to minus A now.
Oh, that middle one is not matching.
So it has to be 0 only. Only middle one is not matching. Otherwise, all the entries are minus A entries only. So that's why we have to keep this middle entry as not, you don't call it middle, call it as diagonal. Diagonal entry should be 0.
Diagonal. 0. Okay.
Okay. So you
Ma'am,
can
one
derive it
question
also.
here regarding this Q. What we are saying, A will be equal to transpose of A, and then we are negating it. So if we are taking diagonally 1, 1, 1, and when we are doing minus, so it will be like all diagonal will be minus 1. So, okay, it's not matching with A. Okay. Okay. Got it, ma'am.
You
Thank you.
can prove it. It's one line
Yes,
proof.
yes.
See,
Okay.
Aij. So
So it
what does
won't
this
be
imply?
equal. Yes.
Aij plus Aj. According to this, Aij plus Aj is equal to 0, right? Right or not?
Yes, yes.
Oh, this is not writing properly. A second, okay, I'll write it in oct. I don't have any other option. Okay. No, I cannot write here. Okay, I'll just explain it here.
No, ma'am, got
AI.
it. It's okay. Yeah, I
Okay,
got it.
okay.
We can
Okay,
move.
okay.
Right. Yeah.
Okay, now upper triangular means Aij is 0 for all I greater than j. What does this mean? So upper triangular is, this is upper triangular here. So I is greater than j. That means row number should be greater than the column number. So see this entry. See this entry is 3, 1. So here row number is greater than column number. Column number is 1. So upper triangular means that below diagonal all entries are 0. So this you call it as upper triangular. What is lower triangular? All entries above the diagonal, they are 0. So here I is for row, J is for the column. See, this entry is say 2, 3. 2 is the row number and column is the 3. So here I is less than J. Similarly, you can take this entry. This entry is first row, third column. So I is less than J. So lower triangular means all the lower means the end, you can say the entries above the diagonal, they should be 0 for lower. And for upper triangular, you can say the entries below the diagonal, they are 0. And diagonal matrix is this. The entries above the diagonal should be 0 and entries below the diagonal should be 0. This is diagonal. And comes the sparse matrix. Sparse is matrix is any matrix having lot and lot of zeros. Now, why they are useful in machine learning? See, sometimes we want, fast computations and we want memory efficient. So zero entries will not be stored. And because of many zeros, computations will be very fast. So this is very useful in NLP, natural language processing, where because see, don't consider, because natural language processing you deal with the text, but ultimately it also has to boil down to some numerical vectors. So every word you will represent, or every document you can represent it as a vector of values, vector, or you can say every sentence can be represented as a vector. So you call it as embeddings. So their sparse matrix is very useful. You have sparse matrix over there. Okay, now comes the positive definite matrix. Okay, now if A, so for positive definite matrix, first you have to consider A. It should be real symmetric. Real symmetric means A transpose is same as A. A transpose is equal to A. Okay, then when you call A to be positive definite, when X transpose AX is greater than 0, that means where X is any vector, any non-zero vector. Okay, now consider this A. This is, you can see, is it symmetric matrix? You just take the transpose.
Yes.
What is the transpose of A? First row will become the first column, 2, 6. Second row will become the, is it symmetric?
Yes.
80 is same as A. Okay, now if X is any vector, okay, it's a column vector and it has to be non-zero. So if you take X transpose AX, then you should get it to be greater than 0. I'll show you how. So this is x1, x2. X is a vector because this is 2 cross 2. It's a scalar. Oh, sorry. It's a square matrix. Square means number of rows is same as number of columns. Okay. So this is 2 cross 2. So X vector you should, column vector you should take, and its size also. So there are 2 rows and 2 columns. So column vector should also contain the 2 values.
Sam, can you repeat this one? Positive definite matrix.
Okay, I'm saying if for matrix to be positive definite, it has to be a real symmetric matrix. Real means all the entries should be a real numbers, and it has to be symmetric matrix. As you can see here, this is real symmetric matrix. And now we have to check whether it is positive definite or not. Okay, how will you check it? You take any non-zero vector X, okay, non-zero column vector. It has to be column vector. Okay, take its transpose and then multiply with A, and then the result should be multiplied with X. It should be, you should get a positive value. Okay, let's see for this. X1, x2, you multiply with this. What will you get here? Can you tell me when you multiply this? Okay, first you can multiply this matrix with this also. What will you get? So this is compatible, right? This is 2 into 2. And this is
2x1.
X1 plus 6x2.
2x1 plus 6x2.
okay. You tell me, I'll write. What will you get? 2x1. You multiply these two first. So 2x1 plus 6x2. And then
6x1
6x1
plus
plus
x1 plus
20,
20x2.
20x2.
plus 20x2. Oh, just a sec. Okay. Now this result you get by multiplying these two. Okay, now you have this vector, column vector. Okay, now you have to multiply with this x1, x2. X1, x2. So what will you get? 2x1 plus 6x2, you have to multiply with x1. So what will you get? 2x1 square.
Plus 6x1, x2.
6x1, x2 plus 6. Now you have to multiply this with this. Plus 6x1, x2 plus 20x2 square. So you'll get this value. I hope you are cleared of how do you get this. Because this is, you'll get scalar now. This is one row into two columns. 1 into 2, this is 2 cross. This is x1, x2, this is this. So this is 1 cross 2 and this is 2 cross 1. So this is 1 cross 2. This is 2 cross 1. So when you multiply this, so what is the result? You will get a scalar. This is 1 cross 2, 2 cross 1. So result will be scalar. So that's why you get the scalar. This is just a scalar. Okay. Now you have to somehow try to make it as a square. Because you want that, okay, this is greater than 0. So what do? You take 2 common. 2 common. So what do you get? 2x1 square plus 6x1 x2 plus 10x2 square, right? Right or not?
Yeah.
You have taken 2 common. Now somehow right, these lines, it's terrible. Ten. Okay. Now how will you make it a square? So this is x1 square. Now this is 6x1 x2. Okay. Now the thing is, try to make it a square. So what do you want? X1 square plus 2. So x1 plus x2 square, what is the formula? So here you are
X1
having
square
2ab.
plus 2x1.
So you try to make it what
10x
you
square.
should get it so that it
Yeah,
becomes
I think
square.
we have to split 10x2 square into 9x2 square
9.
plus 1.
Because this is correct, very much correct. Your good observation. So this is 2 into ab because formula is x1. A plus b square is a square plus b square plus 2ab. So if you want, this is your a square. This is your 2ab. So 2 into 3 into x1, x2. So the b is basically 3x2. So here you should have 3x2 square. So you make it a 9. You make it a 9. Okay. So what will you get here? 2 of x1 square plus 6x1 x2 plus 9x2 square. Right? Nine x2 square. Now what is the term remaining? Term remaining is 2x2 square. So you get this basically. So this is a square. This is square. So this has to be greater than 0. It cannot be equal to 0 because x is a non-zero vector. So either x1 or x2 has to be non-zero. Is it fine? How do we get this? So this is just a multiplication you have done. First, you have multiplied this with this, and then you multiply with this. So you got this result. Now you are trying to make it, you have to play a game here. Play along with these numbers. So you took 2 common, so you get inside x1 square plus 6x1 x2 plus 10x2 square. Okay, so this number is always greater than 0. Okay, so you say A is a positive definite matrix. Okay, now what is positive? Semi-definite. Semi will, when you have greater than equal to sign, greater than equal to sign, greater than equal to 0, only then. That means for any non-zero x, if this becomes greater than equal to 0, then you say, okay, it is positive semi-definite. For example, if you take instead of 20, you take here 18. So you can get here x transpose ax as this. Right? Because here, what term will you get here? 18x square you'll get. So instead of, if you have 18 here, right? 18 here, suppose if you have. So here you will get 18x2 square. Now, if you have 18x2 square, you'll take two common. When you take 2 common, so you will have this x1 square plus 12x1. This is 18. And when you take 2 common, you will get this x1 square plus 6x1 x2 plus 9x2 square. So that will be same as x1 plus 3x2 whole square. You will not have this term in that case. So you'll get this. And this can be equal to 0 because it can be when x1 is say 3 and x2 is -1. See, this is still a non-zero vector. When x1 is 3, x2 is -1. So if you take a non-zero vector, some vector, and if it turns out to be equal to 0, see, for other values of x1, x2, it is strictly greater than equal to greater than 0. Okay, so in this case, if you have some x for which this goes to 0, this value, then you say, okay, it is positive semi-definite. Okay, now we have, okay, very important concept, elementary row operations. Can't hear.
No, we can hear.
Real world examples. See, everything boiled down, whatever you are doing, Gen AI, transformation, everything, even text, audio, whatever you can think of, everything boils down to these matrices and vectors. So this is the starting point only. That's why we are doing all this. Okay, now comes elementary row operations. What do you mean by elementary row operations? If you have matrix, okay, if you interchange 2 rows, that means swap 2 rows. So it is a elementary row operation. Addition of constant multiply of one row to another row. For example, you have row 1, okay, or row I. You add to a row I some constant multiple of some another row j. So this is elementary row operation. And then you multiply any row with a non-zero constant, with a scalar, non-zero. So again, so this is k, suppose k ri. So this is elementary row operation. Interchange of rows, swap. Suppose I swap row I with row j. So all these are elementary row operations. Why they are useful? They are useful for finding the ranks. And important point is these are not for rows. They are only for rows. They are not for the columns. Important point. They are not for the columns. You cannot have elementary column operations. Only row operations.
So
Okay.
why it is, ma'am? Why it is said that no column operation?
I'll tell you just a second. I'll tell you. Okay. If you interchange 2 columns, I'll tell you reason for that. Just wait for a time being. Okay. Huh. Now comes another row echelon form. This uses row elementary operations. But before that, let's understand some terms. Now, when do you say the matrix is in REF form? So first is if the rows, if you have any rows of zeros, that means row containing all zeros, they should be below any other non-zero rows. For example, here, this is the zeroth row. It is below the non-zero rows. All these are non-zero rows. So this is also non-zero row because it contains at least one non-zero entry. Okay. So first point is, I hope it's clear. Second point is the first non-zero entry in each row is called as a leading entry. For example, here the leading entry of this row is 3 because it's the first non-zero entry of the first row. Now come to the leading entry of row 2. So leading entry of row 2 is the first non-zero entry of row 2, which is 4. So this is the leading entry. Similarly, for row 3, leading entry is this -4, which is first non-zero entry of row 3, and so on. Now comes the third point. Each leading entry of a row is in the column to the right of leading entry of a row above it. Now, what does this mean? It says, so this is the leading entry of row 2, and it is to the right. 4 is on the right of the leading entry of the row 1. Okay, similarly, leading entry of row 3, it is on the right of the leading entry of row 2, and also -4 is on the right of the leading entry of row 1, right? So even this 6 is the leading entry of row 4, and it is on the right of the leading entries of previous row. See, 6 is on the right of -4, it is on the right of 4, it is on the right of 3. Okay. And all the entries in the column below leading entries are 0. That means, see, all the entries. So these are the entries of first column. Okay, and they are below the leading entry of the first row. So all are 0. So leading entry of row 2 is 4, and all the entries below this 4 are 0. Similarly, -4 is the leading entry of row 3, and all the entries below -4 are 0. And so on. For 6 also, the leading entries of row 4 is 6, and the rows below in the same column, like the entries below the 6 is 0. So if all these properties are satisfied, only then we say the matrix is in REF form. REF form is row echelon form. Now, how will you get this form? It is important to know.
Ma'am, just
So
one
you'll,
doubt here. Can I interrupt?
yeah, sure. Please go
Yeah,
ahead.
so in the third row, what will be the leading entry? Will it be 0 or -4?
No, see the leading entry definition. Now, first non-zero entry in each row. So the -4 is the first non-zero entry of row 3. So this is the leading entry.
But in the third point is written each leading entry of a row is in a column to the right of the leading entry of the row above it.
हाँ तो ठीक है ना, this is fine because see -4 is a leading entry of row 3 and it is on the right of the leading entry of row 2.
Oh, okay. It doesn't have to be immediate. Got it.
हाँ, it does not need to be immediate. Okay.
Ma'am,
Okay.
ma'am, just one
Yes.
thing. In one of the previous slides, you were showing a upper right and upper triangle. Na? It is just similar to that 0, 0, 0 upper triangle, I suppose.
Correct. Very good observation. So this is also, see, leading entries here of row 1 is this, and all the entries below this are 0. Okay. Leading entry of row 2 is 5.
But it should have one row with all the zeros, right?
Huh? No. This leading entry of row 2 is on the right of the leading entry of row 1. So this is also satisfied. So upper triangular matrices, they are in REF form only. So even see this leading entry of row 3, which
All
is
upper triangular are in REF, but all REF are not in upper triangular because it is, I suppose, in that REF is not upper triangular, but all upper triangulars are REF. We can say that.
agree. I'll show you how. You are right. So all upper triangular matrix. So even this is upper triangular now because
But
So
there
this
is a
is not a
condition,
upper
right?
triangle, I believe.
There is one row should be all
Yeah,
zeros,
one row
right?
should be with the
All
zero,
upper
right?
triangular
All zero.
are REA, but this is not
All
upper
are here.
triangular because this is not symmetric.
But there is a one condition, right? All zeros of one row with all zeros, right?
all this is upper triangular now because all the entries below diagonal are 0.
Acha, haan.
This is diagonal now.
Correct.
So all upper triangular matrices are REF, but not converse. I'll show you why. For example, this. Let me first tell you what is REF, then we'll go to this REF. Okay. So now this is the how many okay, this is number of rows is 3, number of columns is 5, 3 cross 5. So we have to convert it into the REF form. Okay. So first you try to bring. Now here it is saying it is 0. But first row, first entry should not be 0 because it is violating the property that the basically whenever you see first 0, so try to swap it with the row which is having first entry as non-zero. So if you swap with this, say, you interchange two rows. So this is elementary operation. You are interchange. Okay. Now what do you try to do? Now this is the leading entry. Now try to make all the leading all the entries below this as 0. So this is already 0. So you don't need to do anything. Now you have to turn this entry to 0. So which elementary row operation will you apply? What row elementary
-2.
operation? So you'll say R3 is same as R3 plus R2 because this is one elementary row operation which said that, okay, just to remind you, this addition of constant multiple of one row to another row. So here you're adding R2, R3 plus R1. You're adding constant multiple of R1 with the R3. So this is elementary row operation. Now if you add these two, what will you get here? You'll get here 0. Okay. Then 8 plus 2 is also 10. 20 plus 0 is 20. 0 plus 3 is 3. 8 plus 2 is 10. Okay. So whenever you have, so this is the leading entry of row 1. If so, your objective is to make these two entries as 0 because entries below the leading entry should be 0. Now, had it been some non-zero, then here also you have to apply the row elementary operation. But here you need not apply because this is already taken care of. It is already 0. So here now, how will you turn this to be 0? So what did you do? You say, okay, let's add to R3, R1. So when you add this R1 to this row 1 to this third row, and then store the result in R3. So 2 minus 2 is 0. 8 plus 2 is 10. So this is R3 plus R1. Okay. Now, what is the next objective? Now here you have got the leading entry of row 2. And it is why it is leading entry of row 2? Because this is the first non-zero entry of row 2 and it is on the right of the leading entry of row 1. Okay. Now, what is the next objective? Next objective is
Bottom element of row 3.
Make it
So it should be
convert
0.
convert this to 0. Now, how will you convert? Tell me what row elementary operations you will apply. You cannot say that, okay,
minus
R3
minus it is written only minus 10
R3.
times of row 2.
Yeah, R3
oh, okay. R3 is R3
R
plus
minus 10 of
minus
R2.
10 of R2. So now you cannot say minus, you cannot say R3 is R3 minus 5 of R1. So here you will land up 0 here, but here you will get some non-zero value. Okay. So whatever leading entry you are looking at, so you're looking at the leading entry of row 2. So whatever operations you are applying So it has to be with respect to the row 2 only. Okay. So how will you convert it to 0? Should you apply this elementary row operation? R3 is R3 minus 10 R2. So 10 minus 10 is, you will get as 0. Then 20 minus 2 into 10 is 0. Okay. Then 3 into minus 10 into 0 is 3. Then 8 minus 10 into minus 1, 8 plus 10 is 18. Now tell me, is this row echelon form and why?
Yes, all
This
the
is row.
leading property is matching now. All the leading numbers are in the next that property.
There are three properties. So first property is the entries below leading and leading entries below the leading entries are 0. So this is the leading entry. It's the entries below it is 0. Entries below, this is the leading entry of row 2 and entries below it are 0. Now consider this. But here we don't have anything below. And this leading entry, it lies on the right. So all these properties are satisfied. So you say, okay, this is an REA form. And note that this is not an upper triangular matrix. Upper triangular matrix is, it has to be square matrix, right? Here you cannot
No
see what is
diagonal.
diagonal. So you only told me statement, right? Upper
Correct.
triangulars are REA but not converse. Okay. Now
Ma'am, why
comes
is
the
REF so important? Why is REF so important?
why? Oh, it is used for calculating ranks. It is used for solving the system of linear equations. It is very useful.
Okay. Okay.
So one more doubt, ma'am. Why aren't we simplifying the last row? Like we can take 3 common out of there. So we can just transform R3 to R3 by 3. I mean, I've seen it in examples before.
We can do it, not a problem. Even if you do it, so it is going to be R3 is R3 by 3. So it is going to be 1. But why do you need to do that? Our criteria of REF is already being satisfied now. So there is no point.
One doubt, ma'am, here. In the last condition of REF is like last row should be all 0, no? So
Need not be why where it is written. It says okay. It says if rows of zeros exist. Okay. Any rows of all zeros. If rows of zeros exist, so they should be at the bottom. That means they should be below the non-zero rows.
okay.
Ma'am, I have a doubt here.
Uh-huh.
Soumya this end. So, ma'am, in
Yeah,
this,
Soumya.
shouldn't three have a zero below it? Like the last condition is not met, right? Three should also have a zero, right? Or
Here you are saying.
yes, yes. Like below three, there should be a zero, right?
Not required.
But ma'am, the last condition, how is it met? There were conditions, no? That all entries in a column below a leading entry are zeros. So,
Okay.
I think it's applicable only if there is a row. There is no data, right? So it should be fine.
So this is not leading entry now. I don't know why voice is echoing.
so three in the last row, three will be the leading entry, or it's not the leading entry, is it?
No, this is leading entry only. But we don't have any entries below it.
Okay. So in such a case, it need not be like a zero. Right?
There's no need to turn. Like we
Okay.
cannot make it to be zero.
Okay, understood, ma'am.
Okay.
Ma'am, I have a question. Sorry. We just swapped the immediate row, right? Can we do it with the third row also, like in the first step?
Sure. Yes, you can do. So you are saying swap row 1 with row 3. You can do it.
Right. It need not to be an immediate row.
It need not be immediate.
Okay.
Okay, one more point I want to make. What is the rank of matrix? Rank of matrix is number of non-zero rows in REF. For example, here, The number of non-zero rows in REF is 3, right or not? So the rank of this matrix is 3. Do you agree or not?
Yes.
Good. Rank is just the number of non-zero rows in REF form. Okay, let's see about this. Now tell me what is the rank of this?
4.
4. Okay, this is 4. Because 4 are the number of non-zero rows. So just see the number of non-zero rows in REF form and then you can derive the rank. Okay, one more concept is RREF. Then I'll stop. We'll continue tomorrow. Okay, so how do you get RREF form? So it is derived from REF form.
Just one thing.
Yes, yes.
What is that? Like, if you go back to the rank slide, what is like the geometrical significance of that particular like rank? Why we are finding this? What it denotes? What is source?
Rank is
Geometrically.
useful for geometric interpretation. Okay, rank is basically useful for finding the finding the solution of system of linear equations. That I'll do in the next class. Okay, so because there we compute the rank. Okay,
Fair enough.
so
Okay. Yeah.
Ma'am, I also had one doubt, if I may.
yeah.
Yeah, so I wanted to understand, is it necessary that to get to this REF format, we make use of only the rows? Like the computations should be done on the basis of rows and nothing else.
Yeah. Only row elementary operations. Column will not get you anywhere.
Why is that so?
Why it's that? I'll tell you because see, using row elementary operations, you can get determinant. But if you perform column in elementary operations that I'll show you in the next class, you will not be able to get. Suppose I have to calculate a determinant. I'll show you in the next class. So only if you do the row elementary operations, see here, you will get the determinant value, correct determinant value. But if you do the column, they are not, we don't have in, what do you say? Those are not valid operations. That's what I'll say. Okay, let me go to this RREF, then I'll stop. Was okay. Now we have seen this REF form. Now what is reduced row echelon form? So here what we have is the leading entry should be in each row is 1 and each leading 1 is the only non-zero entry in its column. See this. This is RREFM form because the leading entry of each row is 1. Okay. And each leading 1 is the only non-zero entry in its column. For example, this is the only non-zero entry in the first column. This is only the non-zero entry in the second column. And this is the leading entry of row 3 and it is the only non-zero entry in it in the third column. So this is the RREF form. But we don't expect you to calculate RREF form because only using REF you get the rank. You don't need to perform any more because RREF is derived from REF only. Okay. And RREF is unique. Okay. So you can do it in octave also. See, for example, here. Suppose A is we can take some complicated big matrix 5, 4, 1, comma, 10.
Ma'am, while solving a system of equation, should we should we do the RREF method or just REF?
REF. That's why I'm saying RREF is like even if you should just know how to calculate REF. RREF is further you apply elementary row operations on REF to get RREF. But for solving system of linear equations, I'll show you in the next class. Only REF form is sufficient. Now, if I say RREFA, let's say what we'll get. octave you can solve it. Okay, so here again you compute the number of rows, compute the number of non-zero rows. So this is 3. So this is equal to the rank. You can compute the rank also. Rank of A. So this is 3. Okay. So you can apply the row elementary row operations here. For example, A of. So here this is the leading entry. Okay, now you have to make this entry as 0. See, A is this. Okay, I'll just type. Okay, you have A. Now let's do REF form. Then we'll stop. You have to make this entry as 0. So what operations you will apply? Tell me. This is the second row. What will you do? Tell me now. R.
Minus 7 R1.
R2 minus 7 R1.
So 7 into A in 1 commas. Okay, let's see what we will get. Now let's see what is A. You have got. Not now. What is the next operation? Convert this into. What will you do?
R3 minus 5 R.
Half. This
Or
is
minus
fifth
R4
row.
by 2.
R3 minus R4 by 2.
No. See, that's what I'm saying now. You have, because you are solving
R3
this. R3 is
R3
R3
minus
minus
5
5
R1.
R1. Because you are looking at leading entry of row 1. So you have to do all the operations in step 1 with respect to row 1. Okay. Let's do systematic way. You can do that also, but we will do in the organizing, let's be more structured, because here we are solving this like leading entry below the entries below the leading entry of row 1. You should make them as 0. So we'll just, because we are looking at row 1 leading entry, so we'll do the operation involving row 1 only. See, this is row 1. Here also I'll use row 1. Then this also I have to make it 0, 10. So what operation I'll apply? Sorry, what I have written? A3. A3. Okay. Now comes A4. Minus 10 into R1. 10 into A1. Okay, now let's see what is A. Let's execute. Okay, this turns out to be 0. Now what?
Plus
Now
4
again you have,
R1.
this is the leading entry of row 2.
No,
Now you have to
interpret
turn this entry and this entry to 0.
0.
Now you apply. What row elementary operations you will apply?
Or 3.
A of 3
A of
comma
3. Yeah.
R1 into
equal
4.
what? No, don't. Now see, you are talking. Now here we are looking at leading entry of row 2 now. So we we'll do row elementary operations involving row 2 only.
No, we have to make minus 16 as 0, right?
You are right. But we have to do systematic way now. That's what I'm telling. So we don't involve this. If you say minus 16 is 4 into R1. So you say, okay, R3 is R3 plus 4 R1. So what will you
Yeah,
get?
yeah.
Here you will get non-zero entry, which we don't want now, because this is
Okay,
going to be
okay, okay.
4.
Okay, okay.
Yeah,
That's
A3
why.
colon
A
three
R3 minus 4.
minus.
plus
What should I
16
write?
plus 16
Plus 16 or minus? Minus 16 by 20 into A of second. This is because we are turning all the entries below row 2. Oh, below this. Then this leading entry is in row 2. So that's why we are doing operations involving row 2 only. Let's see where we get now. Is it fine? Acha, ठीक है. Now we have to turn this entry to 0. Actually, we have landed up in the fraction thing, fraction business.
Yeah.
Oh, we did not choose good matrix. Anyways, you understood the concept now?
Mm-hmm.
Huh?
Yeah.
No?
Yes, yes, yes.
Yes, yes.
देखते हैं अब, let's see.
So, like
I think
A11 should always be a non-zero
देखो देखो
non-zero
see
entry.
what? See, this is
The
the leading
per-
entry now,
Hmm.
and we have
no,
turned
no,
all the.
no, like few doubts I was having. So A11 should always be a non-zero thing, non-zero entry for REF thing, and all like below the below the row which is having non-zero, which is having all the elements zero, there shouldn't be any non-zero entry below that row. Like these are the two core points.
Zero rows should be at the bottom. Zero
like
rows.
whatever entries are having entries are having non-zero values, that should be the upper, and all the zeros should be at the bottom, at the
हाँ.
downwards, and
Yeah, we,
A11 should always be a non-zero entry.
yeah. If it is zero, then you
Ma'am,
swap with. हाँ.
There are a lot of beginners here, I guess. So there are a lot of things that we are not able to understand from the beginner's perspective. What is
Like.
colon and
अच्छा.
request you
अच्छा,
to
what is
explain.
column?
Yes,
I
please.
told you na, colon is. Hello.
yeah, ma'am, some people are asking me that they are not understanding something. Yeah.
From where did you not understand? This semicolon, it means it is in the another row. Okay, we'll solve by hand. We'll solve by hand. Let's do by hand. Don't need to bother about this. Should we solve by hand?
Yeah, they are asking a colon, not semicolon. What is that colon?
Colon. अच्छा अच्छा ठीक है बस और बाकी सब तो I think everything else is
Yes,
understood.
yes. Everything else is clear, ma'am. She was asking that colon. What
yes.
was
अच्छा
that
अच्छा
thing?
okay it's my mistake ना sorry. See 2 comma colon. 2 means this is the row. Colon means take all the row. मतलब colon means take all the columns. So this A2 is what I'll show you. See 7A2. Second row. See, okay, I'll show you A also. ठीक है? This is your A. Now, if you want to just, because you are doing row elementary operations, so you have to take only rows. So if you have to take second row, so second row is this. So you'll take 2 comma colon. Colon will represent all the entries of which row? Second row. Now if I say this, suppose A colon 1. Now here it means take all the entries of, now this represents, second index represents the column. Okay. So here it will show all the entries of column 1. See, all the entries of column 1. Is it okay?
Yes, ma'am.
अच्छा अब करते हैं, let's, or you will do by hand. Let's stop it. You people might be feeling sleepy. Hope you have understood
Yes,
the
ma'am.
concept.
Yes, ma'am.
Let us start from here tomorrow. That's all.
ठीक है. Let's start from here tomorrow.
Ma'am,
Technically, you can use row operation.
yeah, yeah. Just you can finish, ma'am. Then I have something to
Okay.
say. Yeah.
Okay, I'll just stop recording. So we did today, addition, we saw multiplication of matrices, we saw elementary row operations, we saw transpose, how to find a transpose. We saw special matrices like upper triangular, lower triangular, symmetric, skew symmetric. Okay, I'll just stop.
Yeah.
We'll join.
Ma'am,
Yeah.